Yeah, so this is formalizing the hidden number problem in Isabelle HOL. So this is joint work with Eric Wren, who's just starting his PhD in mathematics at Georgia Tech, and Katherine Kosaian, my advisor. Okay, so the hidden number problem. This was originally introduced by Bune and Venkatesan in 1996. So originally this was for formalizing some bit security results for Diffie-Hellman, but it's sort of become an important paradigm in cryptography in general. So this is kind of really a foundational result. So there are many variants for different cryptographic protocols. So the broad idea, what is the hidden number problem? Suppose we have some oracle, O of t, which yields some information about alpha times t mod p. And the question is, can we recover alpha given access to this oracle? And the answer is yes, with high probability. Okay, so this is the broad idea of the hidden number problem. So for this talk, I'm actually going to briefly review Diffie-Hellman. I think most people will be familiar. So we'll cover Diffie-Hellman and then give an intuition for the reduction from Diffie-Hellman to this hidden number problem, which kind of shows its importance. Then we'll give the hidden number problem formal statement or formal-ish statements. We'll talk about the high-level proof idea, our formalization strategy, and then finally talk about some details. Okay, so Diffie-Hellman key exchange. Suppose we have a public generator G of some group, and generally we're going to be working in this Z mod PZ multiplicative group. So the goal is to establish a shared key between two parties, right? Alice and Bob, we want to establish a shared secret. And the idea is that G to the AB is hard to compute, even if you know G to the A and G to the B separately, right? So at the beginning, Alice, Bob, and this adversary, which can intercept communication, everybody knows G. Now, Alice can generate a secret number A, and Bob can generate a secret number B. Now, Alice can compute G to the A. Bob can compute G to the B. And now I had some animations here, but with the PDF, they won't show. But the idea is that Bob can send G to the B to Alice. Alice can send G to the A to Bob, right? And the adversary will intercept this. So now Alice can compute G to the B to the A. Bob can compute G to the A to the B. Both of these equal G to the AB. So this is our secret key. And the idea is the adversary, it's difficult for the adversary to actually recover G to the AB given G to the A and G to the B separately. Right. And actually, okay, so the adversary would have to solve the discrete log problem to recover this G to the AB. And we assume that discrete log is hard, right? But okay, even under the assumption that discrete log is hard, is it possible to gain partial information about this secret key? And so the answer actually is yes, it's hard to gain partial information. So the idea is that we'll reduce the problem of solving for this G to the AB given a bit leaking oracle. Okay, so we have this Diffie-Hellman function here. I mean, this is essentially what we're trying to compute. Given G to the X, G to the Y, this function gives you G to the XY. So suppose we have this algorithm. Suppose we have some algorithm which can compute the most significant bits of this Diffie-Hellman output. MSBK, well, this is not quite the most significant bits. We'll talk more about how this is defined, but essentially think of it as k bits of information. So suppose we can get some information about this Diffie-Hellman key. So given this algorithm A, well, we're trying to solve for G to the AB. We know G to the A, we know G to the B, so we can compute G to the A plus X and G to the B and feed this into the algorithm. And if we sort of unfold some definitions here, we'll see that we end up with the MSB sub k of G to the AB times G to the B to the X. So G to the AB, this is our hidden number. This is the key we're trying to recover, right? So we can kind of abstract this. We can think of that as just some alpha, some element of this group that we want to recover. G to the B also is just some element of the group. We can call that H. So we have this alpha H to the X. And H to the X, again, well, that's just some element of our group. So we can think of this as just an alpha T. Right? So this is kind of the abstraction from this Diffie-Hellman problem to this abstract hidden number problem. So this is actually going to be our oracle. Right? We're going to suppose that we have this oracle which can compute or which gives you some information about alpha times T. And the point is that we can recover alpha given this oracle with high probability. Okay, so formally, what is this saying? Suppose we have this hidden number alpha, and suppose we have this oracle which computes or gives you some information about alpha T. Here I'm writing mod P explicitly. And suppose that we've sampled some TIs, T1 through TD, uniformly from our group. The claim is that there exists an adversary such that, all right, what is this saying here? basically, if we feed the adversary the input-output pairs, giving each ti to this oracle, the adversary can compute alpha with high probability, right? So we can very likely recover alpha. And in particular, we want to do this in polynomial time. And I'll quickly just note some details here for these numbers. So n is going to be the number of bits in p. Now, this theorem in the original paper, they state this for large enough n, right? So we formalize this to be greater than 961. And this is a reasonable bound. Typically, when you're working with cryptographic protocols, you'll have primes with much more bits than 961. So this is fine. D and k are also relatively small. OK, so what is the proof idea? So the idea, how does the adversary actually extract alpha? How does it find alpha? So we're going to construct a vector u consisting of each of the outputs of this oracle. And OK, recall that this is the definition of our oracle. It gives some information about alpha t mod p. And the point is the oracle, the value of the oracle at ti will be approximately alpha times ti minus some multiple of p, right? That's this mod p. And because we have some information about this, this is an approximate equality. And so we're going to approximate this alpha using lattice methods. So I've sort of plugged in that approximation to each of the components of U here. And the idea is we're going to build a lattice from some basis. So what is this basis? The first d vectors in this basis are going to be essentially the standard basis scaled by p. And then we're going to have one more basis vector, which is just the inputs to the oracle, and sort of forget about this last coordinate. This is sort of a technical detail. But the point really is that if we build our lattice this way, an arbitrary vector v in the lattice will look like this. And notice the form of u and v look the same, right? They have almost the same form, ignoring this last coordinate. And so sort of the key insight is that if u and v are close, then alpha and beta are likely congruent mod p, right, with high probability. And so from beta, then we can extract alpha. So really, the goal is to find this v, which minimizes the distance between u and v. And actually, this is called the closest vector problem. So this is NP-hard in general. But there's a way to approximate it. So Babai's nearest plane algorithm approximates this. Specifically, it's guaranteed to find a vector in the lattice such that the distance between this vector that we found v and the target vector u is close to optimal, right? So we have some fudge factor here. Okay, so this is the overall idea of the adversary. We get our input-output pairs. We generate our lattice. We apply Babai's algorithm. And from the output of Babai's algorithm, we can extract this beta. And hopefully, likely, this beta will be congruent to alpha. So we can extract our alpha. OK, so the main goal that we need to formalize, the way this proof proceeds, we want to show that with probability at least 1/2, every vector in the lattice for which beta is not congruent to alpha, so these are like the bad vectors in the lattice, we want to say that these are all far from u with high probability. And so therefore, if we find a close vector, then the beta will be congruent to alpha. So of course, we'll need to formalize Babai's algorithm for this. We also need to do a lot of probabilistic reasoning. And there's also just arithmetic, for example, this for large enough n and other probabilistic bounds that show up. So these are all sort of these formalization challenges. Now, for Babai's algorithm, luckily, in Isabelle, we already have a formal LLL algorithm. So there's many authors on this entry, including René. So this is a good reason for us to use Isabelle. I believe this has only been formalized in Isabelle. We also need to do probabilistic reasoning. So there's quite a strong measure for math functions and sort of expressions. We'll talk about that later. So this is very useful. And for the arithmetic, well, of course, we all love the Isabelle automation. OK, so I want to talk about some details in our formalization. OK, so the bounds on Babai's algorithm. We're algebraicizing a proof by Stevens, Davidovich. You'll see in the literature are somewhat geometric in nature. You'll talk about hyperplanes and projecting vectors onto hyperplanes and stuff. So of course, we have to turn this all into algebra. And I want to talk about the bound specific. The v in L that minimizes this distance. OK, so I think the best result in the literature has something, the fudge factor is something like 2 to the dimension of L over 4.6. So this is quite strong. But typically in the literature, you'll see something like dimension of L over 2 in the exponent. Actually, so this is not strong enough for our HMP result. This is not strong enough for our proof strategy, and in the original paper as well. So in the original paper, the authors use dimension of L over 4 in the exponent. So proving these stronger results, improving from dim L over 2 to dim L over 4, this requires a lot of tinkering with the parameters and requires a much more technical proof. We kind of wanted to avoid this, so the final result we end up with, it's a little bit ugly, but we have the square root here, the base is 4/3 instead of 2. The exponent is still dimension of L over 2, but this actually turns out to be enough. So we can avoid sort of the really detailed tinkering to get these better bounds. We have a simpler proof, but this still suffices. So yeah, another thing I want to mention, informally, it's kind of clear that this value here is well defined. And okay, in Isabelle, the min is only for finite sets. This is not a big deal. We use inf instead, so that works for infinite sets. But there's still a point here. So in the proof, at least in the literature, the standard proof, you need to obtain a V0 in the lattice, which actually witnesses this sort of minimal distance. And it's, again, intuitively easy to see that this V0 should exist. I mean, the lattice is discrete. We're not going to have accumulation points or anything weird like that. But it might be annoying to formalize. I mean, you might have to introduce some Bolzano Weierstrass or something, talk about analysis. So we kind of wanted to avoid this. So instead, we opted to obtain this V epsilon, where the distance between V epsilon and U is less than or equal to 1 plus epsilon times D, right? And this exists by the definition of inf. And so this 1 plus epsilon times D, and we can do this for arbitrary epsilon greater than 0, of course. So this 1 plus epsilon trickles down into our final bound, but because epsilon was arbitrary, we can remove this. So actually, this makes our proof a little simpler, and we get just as strong of a result. Okay, so also in the literature, yeah, Babai's algorithm, typically you'll see in the literature it's described for real lattices. Of course, we don't really compute with real numbers. I mean, we'll be doing something with rationals. Actually, so LLL is only formalized for integer lattices, so we also have this restriction. But we can, of course, scale any integer, or excuse me, any rational lattice can be scaled to an integer lattice, right? And so we do use this trick. We have, remember, this 1 over p in our lattice. We scale everything by p, so we end up with an integer lattice. And in general, you can take your target vector from Qn. Also, in the literature, we often have d less than or equal to n, so the dimension of the lattice can be less than or equal to n. Actually, so for our proof, we used a change of basis matrix, which was required to be invertible, in particular square. So we kind of tried to lift our results to the d less than n case, but this turned out to be difficult, so we are restricting to d equals n here, so this is somewhat of a restriction. And yeah, like LLL, our Babai's algorithm is executable. So, okay, formalizing the hidden number problem itself. So this is essentially the bulk of the mathematics in the paper. It's one page. It's quite terse. So yeah, the informal proof was about 1 page. Our formal proof, about 4,000 lines of code. This is for just the hidden number problem, excluding Babai's algorithm. So there's definitely a de Bruijn factor here. So of course we're clarifying, proof steps, lots of proof steps, in fact, definitions, clarifying exactly what these definitions mean, and then there's also lots of bounds in arithmetic. I think many people will be familiar with arithmetic and theorem provers is not necessarily the cleanest or the shortest thing, right? Okay. Yeah, so one thing I want to talk about, counting. Counting is always difficult, right? So in the original paper, there is, in the argument somewhere, we have to talk about the cardinality of this set, and it doesn't really matter what the set is here. Kind of what I want to point out is that the original argument shows that the cardinality of this set is equal to this expression involving like floors and ceilings and stuff, and then we bound it below by something that we want. And we looked at this, and actually the floors and ceilings introduce a lot of edge cases. Showing this equality is actually quite annoying. You have to know something about p and know something about mu and do some casework, and this is not pleasant. So we kind of just abstracted this. If you replace the bound in the set comprehension with just a b, you can show that the cardinality of this is less than or equal to 2b, and this turns out to actually be sufficient for what we need. So this simplifies our proof. It's actually a weaker result, but it's sufficient for what we need, right? This is just a little lemma, and it's simple to formalize, right? So yeah, we're happy with this. Also, the MSBK definition. So I mentioned this before, right? What is the MSBK? Really, it gives some k bits of information about its input. So the original paper introduces it as this. So MSBK of x is a unique integer t, such that what, t minus 1 times p over 2 to the k is less than or equal to x less than t times p over 2 to the k. I mean, this is division with some floor or something, right? It's essentially. Actually, so we can kind of think of this as almost a right shift by n minus k bits. Well, it's not quite. There's this p that shows up here, but think of it as a right shift. But then, so the paper introduces this definition that says, actually, we really want to assume this inequality here. We want the distance between x and the MSB sub k of x to be less than p over 2 to the k plus 1. This is really the inequality that we're going to use in the proof. And so we can think of this as really a right shift followed by a left shift, right? So when you right shift, you're losing some information. You left shift, you don't gain information, but it makes this inequality satisfied. And again, it's not technically a right shift or a left shift, but you can think of it like that. And the original paper doesn't actually describe how you can translate this original definition into one that satisfies this inequality, but we've introduced a definition in our formalization that does this. And actually, we discovered, in fact, you really only need p over 2 to the k in the proof. So we work with that instead. So our approach here, yeah, I mean, we sort of wanted to avoid thinking about the details of the MSB operator, like how does it actually work. We really only need, again, this assumption, right, this inequality. So we can work in a locale which fixes this operator and makes this assumption. And then we can instantiate this locale with any sort of definition that we'd like. So in particular, we do use the original definition modified to actually fit this inequality, as well as we do formalize just a simple, a literal right shift followed by a left shift. And this works as well. So there's no need to introduce sort of a more esoteric MSBK. So also probability. So we were doing a lot of probabilistic reasoning. So Isabelle Hall, in the libraries, they have this PMF monad, which gives you a nice do notation. This is often called the Geary monad. And so we can formulate our cryptographic game as a probabilistic algorithm. So this is our game here. So what is this doing? Saying, given your adversary A prime, we want to sample some t's from the set 1 to p minus 1. Then we want to compute the oracle on each of these t's and feed it to A prime. And then hopefully A prime outputs alpha. Right? We want to check the probability that A prime outputs alpha. And so we're doing this using this do notation. And in general, not just in the definition of this game, but in our proofs, we often use this pattern, do sample x from some probability distribution p, and then check some condition capital P of x, right? So sample some x and then check something about x. And we found that it was actually a little bit difficult to reason about inequalities using this expression. So we had to prove some probabilistic lemmas for these expressions. Now, there were plenty of measure theoretic results already in the Isabelle library. So again, the Isabelle libraries are very strong, have a strong support for measure theory. But we found that they didn't really apply well, at least immediately, to expressions of this form. Sledgehammer was sort of struggling with proving anything about these things. So we proved some lemmas which operate specifically on expressions that look like this, essentially lifting these measure theoretic results to this level of abstraction. And so we found that of probabilistic reasoning just using these expressions without having to dive down into sets and talking about measures of sets and stuff. And also Sledgehammer performance greatly improved. Once we had like even a small set of lemmas, it could reason about these expressions quite well. Okay, so the last thing I want to talk about, this is just something kind of cute. So yeah, what does it mean for alpha to be a hidden number, right? Really, it means the adversary doesn't know alpha, right? And I mean, we're fixing alpha in a locale, and we're also defining the adversary in a locale. And if we define them in the same locale, well, the adversary could just return alpha, and that would be cheating. And of course, you can sort of use manual inspection to determine that like the adversary doesn't just return alpha, but I don't know, somehow manual inspection is not satisfying to me. It's not really in the spirit of formal verification. But at the same time, there's nothing really formal that defines what it means for alpha to be hidden. So really what we do is just use a locale hierarchy, and we make sure that the adversary is defined before we actually fix alpha. Now this is a really small thing. Somehow I think it's interesting because making this change doesn't change anything logically. Like it's still the same logical statements, but it changes sort of the manual verification, the amount of work needed for manual verification. I don't know. This just, it's cute. It tickles my brain, so I wanted to mention this. Okay. Yeah, so those are some of the details. Future work. So I am interested in exploring sort of further library support as well as automation for reasoning about these game-based probabilistic reasoning. So again, there's a great support for measure theory and probability, but working with some of these do expressions we found to be a little difficult. So I think there's room for better support there. The hidden number problem itself, so there's lots of extensions, elliptic curve, extended hidden number problem, modular inverse. There's lots of these variants of this hidden number problem. So all of these are, interesting targets for formalization. Also the time complexity. So I mentioned briefly that we want the adversary to run in polynomial time. Actually, we don't formalize the complexity. So this would be reasonable future work. In particular, we would need to formalize the complexity of Babai's algorithm, right? That's the main component of the adversary. Luckily, the LLL entry does formalize the complexity of LLL. So this is a reasonable goal. It would still, take some work, but it's definitely doable. This gap needs to be filled. Okay. Yeah, I think this is everything I wanted to talk about. So thank you for listening.